Very good morning to everyone. So we are continuing our topic, that is benzene and its derivatives. Today we are going to learn about reaction of benzene and its derivatives. So let's get started. First, benzene has 4 degrees of unsaturation. That's why making it a highly unsaturated hydrocarbon. So we are already know that benzene has 3 double bond. That's why it's a unsaturated compound. Number 2, whereas unsaturated hydrocarbons such as alkene, alkyne and dienes readily undergo addition reaction, but benzene does not. We have to find what are the reasons behind it, why benzene does not go for addition reaction. Okay, now see, ethylene and alkene easily go for addition reaction. Here addition of bromine take place. Now whenever a addition reaction take place of any hydrocarbon, that compound loss is double bond or triple bond. You can see that there is double bond is there. After addition reaction there is no double bond is there, all are single bonds. Now in case of benzene also same thing is happened, but benzene is a cyclic compound. Benzene is a cyclic compound and it's having 3 double bond. So addition reaction can take place any of this favorable position. Now after completing the addition reaction, you can find that benzene lost one of his double bond. It's lost one of his double bond. Here is double bond is there before the addition reaction. After addition reaction it lost his double bond. So that it also lost his aromaticity, because it lost his double bond means pi-electrons. So it also loses aromaticity. Now it is a non-aromatic compound. Now benzene first before the addition reaction is a aromatic compound. After addition reaction, after losing its double bond, after losing its pi-electron, it's become a non-aromatic compound. We all know that aromatic compound is a more stable compound in our chemistry. So our benzene become a less stable compound after addition reaction. So this thing will not be desirable for benzene. Okay, now benzene undergoes electrophilic substitution reaction. So here is our benzene. It's having 3 pi electrons. It's having 3 pi electrons. There is 3 pi electrons. So naturally it having lots of electrons. So it's a electron rich area. And here is our electrophile. This E plus, it's our electrophile. It's a electron loving, or you can say it's wanted more amount of electron. Now this electrophile, this E plus, that is electrophile, attacks the benzene. Attacks the benzene because it's a electron rich area, and this electrophile substituted the one of its hydrogen atom from it. So here is benzene, it is a carbon atom is there. So every carbon atom having one hydrogen itself. Here is 2 bond, here is 1 single bond, and here is remaining 1 bond is there that contain an hydrogen atom. Okay, so this electrophile substituted this one of hydrogen atom from it. So finally substitution reaction is completed and this hydrogen atom leave from as a electrophile from the benzene. Now you can see that after electrophilic substitution reaction, benzene still a aromatic compound and still maintain its stability, nothing loose at all. So that's why benzene undergoes electrophilic substitution reaction instead of addition reaction. So here is another example, halogenation of benzene by bromine. Okay, so here also you can see that benzene ring is remain unchanged. It's maintain its aromaticity and it's highly stable. Okay. Now, one more important thing, benzene does not react with benzene alone, but only in the presence of FeBr3, that is our iron bromide, is a Lewis acid, and the reaction is substitution reaction. The type of reaction is substitution reaction, not an addition reaction. Okay, now which type of electrophilic substitution reaction possible for benzene and its derivatives? Let's see. So here is our benzene. There are lots of electrophilic substitution reaction possible for it, like halogenation by chlorine electrophile, bromine electrophile, or iodide as electrophile for halogenation process. Next, sulfonation. For sulfonation process, SO3 electrophile is required. Next is nitration. For nitration electrophilic substitution reaction, we require NO2 electrophile. Next, Friedel-Crafts. Very important. For Friedel-Crafts electrophilic substitution reaction, we require CH3 electrophile or C2H5 electrophile. So we going to learn about all these things one by one. So first of all, another more important thing that we can break the double bond of benzene if required in any case, just following some condition, like in high temperature, catalyst is there, and critical condition situation. So all these things are maintained, so then we can also break the benzene's double bond easily, but the compound become less stable and lost its aromaticity totally. Okay. Now, what are the steps involved in electrophilic substitution reaction? First step is generation of electrophile, second one is attack of electrophile, and third one is removal of old electrophile. All these three steps are common for any kind of electrophilic substitution reaction. So today we are starting from the halogenation of benzene. We take example for chlorination of benzene by using chlorine electrophile. So here it is our benzene, here is chlorine atom, reaction takes place, and after completing the halogenation, that is chlorination of benzene, we get the chlorination of benzene product, that is chlorobenzene, with the help of anhydrous AlCl₃, and we also get a byproduct, that is HCl, that is hydrochloric acid. So here AlCl₃ is a nothing but Lewis acid, and in this reaction it is act as a catalyst. So what is Lewis acid? A Lewis acid is a chemical species that contain an empty orbital which is capable of accepting an electron pair from a Lewis base to form a Lewis adder. So actually this one is a single step reaction, but we have to learn about reaction mechanism and what are the steps involved in this reaction process. So we learn about one by one. Okay, so what are the mechanisms behind it for chlorination of benzene by using chlorine electrophile? So now the first step, that is our generation of electrophile. So starting from chloride atom, so we all know that it is made of two chlorine molecule by sharing one electron from each and make a single bond. Suppose this chlorine molecule takes the electron from another chlorine molecule like this by fusion or heterocyclic cleavage. So one is become Cl plus, that is our electrophile, and another one is become Cl minus, that is a nucleophile. But why the fusion or heterocyclic cleavage take place? Because in your reaction one Lewis acid is there. This Lewis acid promotes the fusion or heterocyclic cleavage. In Lewis acid definition, we found that these compounds having an empty orbital capable for accepting electron pairs from a Lewis base. So this one our Lewis base, and having a complex like AlCl₃ minus, and this complex is essential so that the reverse of fusion it not take place. So this one is very essential. If the reversible is possible, then again it will become a Cl₂. If reversible is possible and this Lewis acid is not there in our reaction, then it will be reversible the whole mechanism and it will become Cl₂. Okay, sp pair again and we fail to chlorination of benzene. Okay, and finally we get our electrophile. So this one all about your step 1, that is generation of electrophile. Now for step 2, that is attack of electrophile. Now in benzene also same thing will happen. Here is one carbon is there and here is another one, double bond is there, sharing electrons making a bond. Now here also fusion takes place and this carbon takes electron from this one. In presence of electrophile, that is Cl plus, which one just prepare now. But before fusion take place, all position in benzene atom, there is 1, 2, 3, 4, 5 and 6. There is all position in benzene having equal amount of electron. But after fusion process, this one means this carbon having excess amount of electron because it takes electron from another carbon. It takes electron from this carbon. So this carbon is electron rich area more than others. That's why electrophile attack on that position only. So this electrophile is attack only on that position, particularly for electron rich area. So finally we get this type structures, or you can say intermediate state all over, because benzenes having delocalized pi electron. For resonance we find some more intermediate structure like this. So all of these are intermediate structure for resonance. And we can write like this structure as a hybrid structure, because this pi bonds, or you can say the double bonds, it can be delocalized one after another through resonance. So we collectively like draw this structure, hybrid structure, okay, by the dotted line. So all are this intermediated structure, and this one all about your step 2, that is attack of electrophile. Now we go for our last step, that is removal of old electrophile. So we get this intermediate structure in our second step. Here the double bond is break, and this carbon atom having one hydrogen atom with its other carbons having also hydrogen atom with its. So this hydrogen atom removed from there by donating its electron, to this carbon atom which having deficiency of electrons. So hydrogen atom removed from the benzene as a electrophile, because it's donate its electron, so it's also have deficiency of electron, so it's removed from benzene as a electrophile. So this one is our removal of old electrophile. So this one is our removal of old electrophile. But why this happened? Because in reaction a catalyst is there, that is our Lewis acid as a form of AlCl₃ minus as an intermediate state. So it's remove chlorine ion Cl minus, remove chlorine ion from it. So this chlorine having electrons share its extra electron to the H plus, that is our electrophile, old electrophile, and making a product that is HCl. And also AlCl₃ is remain same because it's a catalyst. This AlCl₃, it's a catalyst. We know that catalyst just fast forward our reaction process, but it's remain same at the end of the reaction. Okay, so after removal of H plus, the deficiency of electron of the carbon atom is fulfilled, the need of this carbon, and this here is the double bond, which one we just lost, it automatically generate again. So here it's our product of chlorination of benzene. So it is nothing but our chlorobenzene. Okay, so this all about the mechanism of chlorination of benzene. Okay, so for today's class that is enough. Thank you everyone.